Hello everyone. So in this lecture we are going to quickly review the graphs and the graph traversal method, because in the upcoming lecture we are going to talk about some algorithm that is based on graph. So to start those algorithms, like finding the shortest spanning tree, or to find out shortest path given the graph, we need to know what the graph is. So this lecture is basically a quick review of the graph and the different properties of graph that is required. Okay, so let's start. So graph is something that we are frequently using it to represent our problem. So whenever any problem is given to us, we always try to make a graphical representation of it. Like we used to show the flow of the program by using a flow chart. We are using graphs to make a topology, or to represent a topology, like a star network is there, ring network is there. So whenever you are going to configure your network or your structure within your organization, you are again using graph. We are calling as a topology. We are also representing different problems using the graph. Example, graph can be very much efficient to represent the different rail routes, or the different routes to reach to any position. So graph can be used to represent many different kind of problem. As you can see, there is one problem called binary relationship. So here you are representing x is a proper factor of y. So here you can see that these are the numbers, that 2 is a proper factor of 6, of 8, and 1 is a proper factor of 2. And so there are many different problems may exist that can be represented using a graph. So graph is a very powerful tool, you can say, to represent our problem. We have different kind of graphs that we used based on the different problem given to us. So we have one type of graph is called directed graph. We also call it as a digraph. Graph in general is a collection of vertices and edges. So we represent using uh, this notation G equals to VE, where V is a set of vertices, or you can say V is something which is a set of vertices. Let's say V1, V2, and Vn, and E is a set of edges. You can write it as E1, E2, and En. So we can represent graph as G equals to VE, where V is a set of vertices and E is a set of edges. Now we have certain properties. Vertices are also called as nodes. Okay, elements of E are called edges. So we have a set E which consists of many elements, and we are calling these elements as edges, or directed edges, or the arcs. For a directed edge, VW in E, V is a tail and W is its head. So whenever we talk about the directed graph, in directed graph we are having an edges which is associated one order, one direction. So if you write any edge like this VW, so that means this is a tail, V is a tail, and your W is a head. In text we simply write VW. So when we refer to any edge, we simply write VW, but actually it means that it starts from V and it goes to W. One thing to keep in mind whenever we talk about directed graph, then uh, then VW and WV is a different meaning, because these are the ordered pairs. So if I say VW, it is not equivalent to WV. When we talk about indirected graph, then in that case both are assumed to be same thing. Now this is undirected graph. It is most of the properties are very much same like the directed graph, but we have some differences. Let us see what are this. So here again we are defining the graph as a pair of V and E. It's a set of V and E, where V is a set of vertices and E is a set of edges. These set of vertices means this V consists of many elements we are calling as the vertices, and these are also called as nodes. Each edge consists as a subset V containing two elements. So whenever we talk about the edge, so edge consists of two vertices. Whenever I say one edge, So it has two endpoints, and these endpoints represent the two vertices. So every edge represent the two vertex. VW denotes an undirected edge. So when we say VW, that means there is an edge whose one ends is having a vertex V and other is having a vertex W, and there is no ordered associated with it. So you can write VW or WV, both is having a same meaning. It actually means that there is a path available from this node to this node, and we write this via line only, and there is no arrow associated with this. So just to revise that, when we say like this and when we say like this, then this is for used for the directed graph, this is used for undirected graph, and we simply write VW or WV, both has the same meaning. Then we have something called weighted graph. So far we have seen that graph we are defining as a set of vertex and edge, but now in the weighted graph we have added one more component to it, that is W, and W is a weight assigned to any edge. So let us read. W is a function from E into R. So W is basically a function that defines every edge a real value. That means this weight can be any value which can be a real. So when you use this function and you pass this edge, it will return you a real value. What does it mean? It means if I am having a graph, let's say this is something like this, and these are the edges. Let's say this is edge AB, then this is BC, and let's say this is BD. Okay, and this is assigned one weight 4. So we have a function W, and when you provide any edge to it, AD, it will return you one real value, that is the weight of that edge. So if this is 12.9, now this value refers to the cost. Now cost may be in terms of distance, in terms of time. You may say that moving from A to D, it will require 4 kilometers to walk. So it refers the distance. Similarly, it may also be representing a time, that from moving A to D, it will take 4 hours. So this value refers a cost. So that weight refers a cost that is associated with any edge. So for an edge, WE is called the weight of E. So if I say DB and here the weight is assigned 9, then WDB means 9. This is how we are representing any graphs. We have basically two methods for representing a graph. One is called adjacency matrix representation and other is called adjacency list representation. So first we will see what is adjacency matrix representation. So here a graph is given to us, G equals to VE, and where N represents the number of vertices and M represents the number of edges. Or you can say we have set vertex V where we have V1, V2 up to Vn. We have N number of vertices. Similarly, we have set of edges where we have M number of edges. So M is the number of edges, N is the number of vertices. And if this graph is given to us, this is undirected graph, which is not weighted. No weight is assigned to this. This is simply a connection. So for this, we can make a matrix. Now the size of the matrix depends on the number of vertices. So here, this is for V1, V2, V3. We have 7 vertices are there. V4, V5, V6, V7. This is how we can represent. And whenever you find any edge that connects to the two vertex, then we write an entry, because this is simply a very simple graph where no weight is assigned. So here 1 means the edge is assigned or we have a path, and 0 means there is no path associated. So if you see V1 to V2, there is a path is actually there. So V1 to V2 we will write 1 here. Now keep in mind that V1 to V2 we have a path. Similarly, you can say V2 to V1 we also have a path, because this is not directed graph. So again we have also one entry, V2 to V1 we have this entry 1 here. So you can just look to all the edges and then write the values here. So we'll take one more value. Now if I look at this 2 and 4, so 2 to 4, so you have to read from row to column. So 2 and 4, if you look at this, this is one entry here because this represents this edge, right? Similarly, we have 4 to 2 is also there. So if you look at this 4 to 2, we have. Now what does it mean? It means this is actually a, yeah, mirror image of this side. So if you look at this entire matrix, we have two parts. This is called upper triangle, this is a lower triangle, and then this is the diagonal, and diagonals are 0 because we don't have any loop here. So if I make any self loop here, then we have a path from v1 to v1. We would have put the value 1 here because we don't have any self loop here, so the diagonals will be kept 0. And this is your upper triangle, and upper triangle is just an mirror image of lower triangle. So keep in mind, whenever you are given with the upper triangle status, you can easily find out what is a lower triangle status and how the connections have been made. Now if it is asked that how many edges are there, if the graph is not given to you, you are provided with the what is this kind of matrix, and you are asked that how many edges are there in the graph, then you need to simply look to any of the upper triangle or lower triangle and see how many ones are there. So you can see here 1 2 3 4 5 6 7 8 9. That means in the given graph we have 9 edges. We can count here 1 2 3 4 5 6 7 8 9. So this is how we can represent any graph using an adjacency matrix. Then we have adjacency matrix for a weighted graph. Now here this graph is different. Is it different in two ways? One thing is here the edges as having a direction. So in the previous case, the edges are not directed. It is said to be undirected graph. Now this is having a direction. The second difference here is we are also assigned one value. We are calling it as a weight of this edge. So if this thing is given to us, so instead of writing value 1 and 0, in the previous case we have written 1 and 0. 1 means the edge is provided, 0 means the edge is not provided. Now here in place of writing 1, we will write the weight that actually defined in the graph. So if you write this, this is again v1, v2, v3, v4, v5, v6, v7. So if you say there is a path from 1 to 2, so from 1 to 2 we have an entry that is 25. That means this is the weight of this edge. Similarly, there is no path from 2 to 1. So if you look at this 2 to 1, there is no path. This is infinite. So here we are writing infinite if there is no path is given to us, and we are writing 0 for the diagonal position. So these are certain notations that we are using to represent our adjacency matrix for a weighted graph. In some notations, if the path is not available, we may be writing with 0 also as well, and in some notations we are writing infinite. So it depends that what kind of notation has been used, but most of the time for no path we use infinite, and for the path we write the weight of that edge. So if you look at this, if I look to 6 to 4, so 6 to 4 we have a path and the weight is 32. So 6 to 4, if you look, we have this entry whose value is 32. This represents that from 6 to 4 we have a path. Now do we have a path from 4 to 6? So you have to look at this v4 to v6. We don't have any path and we are writing as a infinite, and we are assuming that there is no loop, so all the diagonal values are 0. Just keep in mind that diagonal represents a loop of any node. Okay, so let's move next. The other method is called adjacency list representation, and this method is actually implemented using a linked list. So far we have seen that how to present this graph using an adjacency matrix, but now we will see that how a linked list can be used to represent our graph. So one thing you have to keep in mind that here you are using list, and then you are also attaching the list with the linked list. So what does it mean? It means we have 7 nodes given to us, so we have to make a list of 7 spaces. So we have here, you can see there we have seven items are there which represent every node, and then with every item we have a linked list attached to it. Now what is this linked list represent? This linked list represent that what are the nodes which are connected to this particular node. So here you can see with 1 you have connected to 2 and 3, so you have to make a node for 2 and 3, and this is how we can represent using a adjacency list method. Now if you look at this, with the 6 we have a direct connection of 3, 4, 5 and 7. So you can see that with the list entry 6 we have the 4 nodes connected: 3, 4, 5, 7. So this is how we can make use of adjacency list. Now keep in mind that when we are representing our graph using adjacency list and our graph is undirected, in that case our node will consist of only two fields. One field we are using it for storing the value, and other field we are using to store the link to the other node. But when we have a graph where we are using directed, and also we are assigned with the weights at the edges. So here the key difference is we are having a weight. Now because of this one more value, we are assigned the weight at these edges. We need to make one more field in our node. So earlier we have two fields in our node. The first field is basically represent the node index, and the next field is actually the connection of the next node. But here we have one more field that actually refers the weight of that edge. So all the things are remain same. Now if you look here, we have 7 vertices, so we have a list of 7 items. Now here you can see from 1 you can go to 2 only, so it can connect to one node, and the node is actually the second node. This is the node index, means the node number, the node identity you can say, and the weight to go from 1 to 2, or the cost you can say from 1 to 2 is 25, and there is no more link, means from 1 you cannot go to any other node. So we have no other node, so this is nil, means there is no further path or the node associated with 1. Now if you look at this 2, now from 2 you can go to 4, you can also go to 3. Okay, so you can go to 3 and you can go to 4. So you can see here from 2 you can go to 3, and you can go to 3 with the weight of 10, you can see here, and also you can go to 4 with the weight of 14, and then further we don't have any other node that can be reached from 2. So this is how we are representing, and here also you can notice that from the node with value 5, this is actually you cannot move from this node to any other node. You can reach to this node by different nodes. By 6 you can reach to 5, but from 5 you cannot reach to anyone. So you can see that in this list the connection for this 5, there is no node, means you are not allowed to reach to any node from 5. So if you find in this list any element who is having a nil value, that means from this node you have no path associated, you cannot move from this node to any other node. This is how we are going to use adjacency list to represent our graph. Then the other thing that comes regarding the graph is how we can traverse it. So when it comes to graph traversing, we have two popular methods. One is called the BFS, which is called breadth first search, and the other is called depth first search. These are very popular method, and already we have discussed in our previous semester. We have already learned this in our data structure course, so I am not discussing again in detail, but just to remind you that when we talk about traversing the graph means you need to go through all the nodes by using some algorithm. So we have two very popular algorithm. One is the BFS. In the BFS, what is happening, you are from any node you are visiting all its neighboring nodes, and then you are moving in this fashion until you cover all the nodes. But in the depth first search, what you are doing, you start from the node and you keep on moving until you reach to the terminal node or to the leaf node. So you just keep on exploring the path up to the up to the fullest, up to the deepest level that can be possible to reach, and then you can explore the next one. And you keep on doing with this approach until all the nodes have been traversed. So these have two different approaches which have been used in different applications. We will see one by one that how these traversing can be used in different way for implementing different ideas or different algorithms. So this is all for graph. This is just a summary of the graph. Now in the next video, we will just rate some algorithm that is to be applied on the graphs. So see you in the next video. Thank you very much for this lecture.